Vlsi Design Lab. First, we are going to design the inverter. So initially, for the prerequisite, we need two softwares mainly and the Java. So one is the electric software. In this, we are going to do all these circuit circuit creations, layout, everything, and LT Spice. This for the simulation of the Spice code which is generated from this electric software. So we require LT Spice version 4. I'm using this, and electric 9.07 version. So all these files like softwares downloadable link is provided in the description. Please go through it. And even you need to install the Java. So first you need to install the LT Spice. If you are the Windows user, simply double click on it. This is just a exe file you can install. If you are the Linux user, you need to use the Wine to install this. Simply right click on it, open with other application. If you already installed the Wine, just type Wine. It will run from the Wine, so you will get the installation window, and click accept like normal way to install this file. Okay, so after the installation of LT Spice, this is the jar file. So we require the Java. Install the Java, and you can directly double click on this to open this software, or else in Linux it will directly open. In Windows I'm not sure, so you need to just open the terminal, and you can simply write java.jar and the file name electric 9.07.jar and click enter. So this will open the electric file, and here one no name library, simply it is created. Simply click on this and close this library. Okay, so now we need to create our own library. In that we need to create all our designs and whatever the experiments, everything. So just go to the file and new library and new library name. So we give as Vlsi experiments experiments and click OK. So now the new library Vlsi experiments is created, and here go to the libraries, right click on it and open, click open, and this will open Vlsi experiments. Okay, so this is the library we just created. Now we need to create the cell, new cell in this. We need to create the schematic as well as the layout of the design. So we are going to design the inverter. So just right click on it and create a new cell. And first we will do the schematic of the inverter. Schematic, and here inverter. Okay, so schematic, it is selected and click OK. And here if you click here inverter schematic and go to the file and go to the preference. Okay, so I just double clicked it, and here go to the technology, and in the technology just okay, so scale, go to the scale, and here we are doing in the scale of 200 nanometers. So I'm selecting MOS 200 nanometers. Okay, then click apply. And another thing, we need to do a small extra requisite is go to tools, and here go to spice, go to the spice bar CDL, and in this you need to do the certain changes. So here initially if something else is selected, we need to select spice 3 and spice level 3, and here yeah, these things. And another important thing, run program, this is required to uh, send this generated spice code to the LT spice to link the electric to the LT spice. We are doing this. So here I'm using the Linux, that's why I use this wine command, otherwise it's not required. These two lines also I will provide in the description. So run program, here you need to specify the program, that is the waveform generator, that program, that's from the LT spice. And here the arguments, in LT spice version 4 it works fine, I checked with that, that's why we are using LT spice version 4. So this is that argument we just need to give. Okay, then click apply and click OK. So these are the initial setup. So this remains same for all the remaining experiments. Then in the schematic, so here we can zoom this, just click here. If you want the grid view, you just need to type Ctrl G. Okay, if you press one time Ctrl G, it will provide these the like grid structures, and that time it will off the grid structure. So now the grid view is on, and go to the components. So first for the inverter we need one PMOS and one NMOS. So this is the PMOS and this is the NMOS. So one PMOS we need. If it is not visible, then okay, I will make it visible. I'm searching for the keys. Okay, so here is that enlargement, enlarge selection. Okay, so this is the for making the this view left and right side, and this is for the enlarge. Okay, so you can do even with the keyboard shortcuts as well as in the mouse. Okay, so now go to the cursor, and this is the PMOS, and NMOS we need to select, and just move to align this. This is the NMOS, and to connect these two using the wires, right, okay, left click on this at this edge and come here and right click. So this will connect using the wire, left click and right click. Okay, so now we even need to connect from here to here. Okay, then we need one voltage source, that is here power source. So this one we need to keep here, just align it and connect this power source, and even we need to connect a ground here. So this is our ground, and from here to here. Okay, so now we need to give the input here, and here we need to take the output. So for that one we are going to select the create node. Okay, so this option, then click that create node here. This is for the input, and this is for the output. Okay, then select just connect a wire between them. So similarly from here. Okay, so now and we are setting its length and width. Just click here, 2 times click in the middle, and width we are setting as length is 2 and width is 10. Okay, 2 and 10. So width is 10 and length is 2. Okay, then similarly here width is 10 and length is 2. Click OK. So we set the width and length now, and here this is the input and this is the output. So click on this. We need to tell that this is the input. So click on it and go to export and click create export, and here we need to give vin, that is vin. We are creating the export, and what is this? This is the input. Click input, click OK. So vin appears here, and you can just drag it anywhere just for the clear visibility. Then this is output. Click on this, and you can use even Control E as the shortcut to create the export. And here v out, click on the output, click OK, and just keep it here. Okay, and we are using the c5 models.txt for the behavior of this NMOS and PMOS, that is the model for this NMOS and PMOS. So that's why we need to set the spice model for these two, NMOS and the PMOS. We need to set the spice model. So select this, just click on this, and go to tools, and go to go to simulation spice. Okay, simulation spice, and go to set spice model. Okay, so here it will give spice model. Just drag like this and keep it here, and 2 times click on it and just name it as PMOS. Okay, and click enter, because it is named in the c5 models file as PMOS. That file also I will going to share with you guys, and I guess that file is okay, we need to have that file, I guess. So c5 models.txt, is it there here? No, it is not there. Let's okay, so I may be having somewhere in my directory. Let's see, c5 models.txt. Okay, I don't have it. Let's download from the we will download it. Okay, we'll download it. So just go to the Chrome and search for c5 models.txt file. Make sure you are connected to the internet. I'm connecting. Okay, so let's download this. Okay, c5 models.txt file. Okay, it will come now, just on the internet. And okay, so here c5 models.txt, this file we just need to download, and yeah, this is that file, c5 models.txt. so here you can see the NMOS naming is there, so you need to name as NMOS. Just Control A, Control C, and go to your Vlsi or any folder, right click on it, create new document, empty document, c5 underscore models.txt. click enter, and open this and paste the things, Control S. Okay, so this is what we just copied, c5 models.txt. Then you can close this one. We have this c5 models.txt, and okay, so yeah, now this is PMOS. Similarly, do the go to the tools and simulation spice, set spice model, and okay, go to just select this and go to tools, simulation spice, set spice model, and here NMOS. Okay, that C5 file also I'm going to share in the description. So now we have this NMOS and PMOS. Now we need to write the spice code for this in order to work. So for that, go to the spice. Here is the spice, right? Go to, no, not the spice, go to the MISC, and here we can have the spice code. Okay, click on the spice code and click somewhere here. So this will display like this. Just click on this and press Ctrl I. Okay, press Ctrl I and go to multi-line text, and here we need to write the spice code. So for the spice code, first we need to give the power supply for this one, that is this V in. No need to name it as a V in and ground. It will default, it will take as a V in. So V in 0. Okay, so 0 DC 5. That means we are giving the 5 volt. So DC 5 volt. So the syntax is, so syntax for this one, that one we can write by using the asterisk symbol. So V is the initially this has to be start with the V. The this is the voltage name. It has to start with the V. That is the voltage name. Voltage name. Anything you can give, and then second one is the, so the point, that means the 2 points. We are giving the voltage source to the 2 points, right? One is ground and another one is the another output. That way, if you take the battery, it will be plus and minus like the 2 points, right? So here also 2 points. So that is n plus and okay, I'm simply call this as n plus and n minus. Okay, so this is not V in, it is VDD. Okay, we supply, right? Yeah, V in means this one. I just confused. This is V in, this is VDD, that is supply. So VDD 0 DC 5. Okay, so n plus n minus, that is VDD and 0, and here the voltage type, what type of voltage, whether it is a DC voltage or AC voltage, that is the voltage type. And here we need to give the voltage, that is the voltage value. So this is the syntax. Okay, so yeah, VDD 0 DC 5, this is default as VDD. Okay, so sorry, initially I told this as V in, this is V in, this is VDD, and this is ground. Default it will take as VDD here, and we give the VDD, and we need to okay, so after the VDD we need to give the V input for our inverter. So V in, we will use the pulse command, so that we can give some, for some time period we can give it as a high, and for some times we can give it as a low. So for V in, okay, so V in and 0 DC, and we are not giving DC. V in 0 and okay, so this is DC, only DC, and here if you write the DC type is already over, but this type is, we need to give pulse. Okay, V in 0 pulse, and here initial pulse means pulsed waves, so it has a initial and final values. So let's first write its syntax, so it will be easy for us to write these like this spice codes very easily. So V, that is the same thing, voltage name, voltage name, and n plus, that is the positive terminal, n minus, that is negative terminal, usually ground we are giving, and here we are using the pulse command, pulse. Okay, so then it follows some parameters like initial value. Okay, so initial voltage, then initially. Okay, so we can give this as a 0. Initially our pulse is at 0, and then we have final voltage. That means the pulse, highest pulse is 5 volt, and so there are some delays. That is the first one is the delay time. Okay, so delay time. So delay time, we don't need any delay in the pulse, so we just give as 0. Then delay time, there are 3 kinds of time we need to specify here. One is the delay time, and next one is the rise. Okay, so that is the rise up time, or rise delay time, rise time and the fall time we need to give. So rise time, if we give 0 also, it will take a small amount of time, so we give this as a 1 nanosecond. And fall time, this also we give as a 1 nanosecond. Rise time, fall time, and then is the time period. That means T on plus T off. How many times, like the T on has to be there and T off has to be there. Time period, T on plus T off. So this time period, we will give this as a 10n. Okay, so this is the time period, and total okay, so this is not time period, this pulse width. Okay, pulse width. That means yeah, I told, right, how many times this pulse has to be on, like pulse width of that pulse. Then this is the time period, that is T on plus T off, that is the time period. So here the time period, simply we can give 2 times of that pulse time. Okay, so anything you can give, it just varies the waveform, input to pulse waveform. So this is what the syntax we need to follow. So fall time, okay, just remember n plus n minus, pulse. Okay, this is the pulse, and initial voltage, final voltage. There are 2 types of the 2 voltages, and then delay, 3 delays. First one is the delay time, then rise time and the fall time. Okay, then is the this one is the pulse width, and then is time period. Okay, so you just need to remember this. And after this we give the pulse command, and what type of analysis we need to do. So first we do the transient analysis. So dot tran, that is the transient analysis, and how many seconds, like so here we have, okay, time period. Okay, so here so to, okay, pulse, it will, how many times we want, like for single pulse will be around 20 nanosecond to time period. So here we will be having around 200, okay, 200 nanoseconds. So this is the syntax we need to write, and okay, so one is the VDD and Vin. This is for the we just comment it out, transient analysis. Okay, so and another thing we need to add, that is the C5 models.txt. I told, right? So here we have the spice like the model, we set it the spice model, so we need to have the reference for that model. So for that we need to set include that c5 models.txt file. So for that okay, just I will comment out include c5 models.txt file. So for this dot include what file we need to add? We need to add c5. Okay, C is capital, I will make c5 underscore models dot txt. Simply just write like this. Okay, we don't know the directory and all, simply just write like this. We will add that file to the same directory where our file is. So dot include c5 models dot txt, that's it. So now click apply and click OK. So this is our code. This comment is actually not needed, but I wrote just for the reference. Then go to file and save library as, and here you go to wherever you want. So I'm just going to my this Vlsi directory, and here I will just create one new folder. Okay, Vlsi, I will just create one new folder. Let it be new folder. So inside this vlsi experiment.jlib, okay, so the extension is jelib, and click save. Okay, now it is saved in that directory. Now if we do like, if we now run this program, it may give some directory error. It is saved. Go to file and save library, just click and close this once, and go to your that directory. Here we have that c5 models.txt. Just copy paste to your this vlsi jlib directory and paste here. These two files are there now. Okay, so whatever we call this c5 models.txt, that will take from this file. So now again run the this electric, or open the electric, and go to file and open library. So choose your this new folder, that your JLib experiment, click open. Okay, so this is to show that it will not give any directory error. So now go to the tools and go to the simulation spice and write spice tech. So if we have any errors, we need to get in the just minimize it here. We will going to have the if any errors, then this will going to give here. Okay, so this is not opening the LT Spice window. Let's check this. So I'm just going to same like in Windows directly it will open. Okay, cannot find. Okay, so LT Spice 4 some directory. Okay, so this is the that directory. Just want to make correct. So I have this LT Spice 4 here, and that's card. This is that program I told, right? This program we need to link. So how I get that path means in that I showed here. Okay, so we need to change, go to file and go to the preferences, and in the preference go to tools, and here spice, and here. So this directory, now this directory is not valid, that's why it is not opening. So this is card 3 is here. You just go to the LT Spice where you installed. In Windows it is maybe in the program files or wherever you installed, and copy the its file path. Okay, so here it's copy its file path and open that, open this, and here we need to, okay, so paste this LT Spice 4 parse card3.exe. just paste that path and click apply and click OK, and you can close this now. And here now if we click, go to tools and go to spice, write spice tech. It will open the spice tool that okay, so just you can just okay, so yeah, this is what the spice code we wrote. So here we have this one, and this is our vin. Okay, so this is our vdd and vin and transient analysis and the C5 models. Okay, so these four things we have, and now let's run this file. Click run, and we need to see the output waveform. Right click on it, click on the okay, so just right click on it and click add traces, and here click vin and click OK. Yes, vin is proper, we are getting the vin. Okay, so this is what the pulse command that's running till 200 ns, 200 nanoseconds, and you can plot the vout directly here, or just click add plot plane, and here click this one and add trace vout. Okay, vout, click OK. So the output has to be the inverted output. So from 0 volt to the 5 volt, yeah, this is inverter. So this is how the inverter is working, and this is the schematic of the inverter. Okay, so in this waveform, now we need to see the so basically we need to see the three things, that is the rise delay, fall delay, and at the beginning how much delay time it will propagation, that TP, propagation delay. So for that so to measure these delays properly, what we can, one extra thing we need to add for our schematic, that is the capacitor. Okay, if we add the capacitor, we can see these delays and all very clearly. So just go to the here, you can close this spice for a time being, you just close this, and click on the capacitor here. Okay, normal capacitor, and click here, and from the this ground to the output, we just need to have one capacitor. Okay, so this is of 1 picofarad. Okay, no, we just have 0.1 picofarad, 0.1 picofarad. Okay, click OK. Then here we just need to, okay, I'm just going to make this up, and here we just need to add this capacitor. In layout, already the layout capacitance will be there, so no need to add, but in this schematic we just need to add this capacitor. Okay, so here, okay, so now it's clear. Yeah, we add the capacitor, just Ctrl S and go to tools and set spice model. So here the condition, three condition we need to observe. So first one is double N is equal to double P, that means width of the NMOS is 10 and width of the PMOS is also 10. So now go to tools and simulation spice, write spice tech, and click here, add a trace vin, click OK, and add plot plane. Okay, so add plot plane, and click here, add trace, and v out, click OK. So now here we can see the length and the width, which is converted to 200 scale, that is 200 nm scale. Okay, so here the technology that we set it, right, MOS 200 nm, so it is converted to that scale. That's why it is not a 2 and 10, it's 0.4 and 2U. So here First thing is, okay, so here we just note down these things. Okay, so I'm just noting down in any text editor you can use. I'm just noting down here. Okay, so let's note down here. First condition is W n, that is the width of the NMOS, is equal to WP. Then what is our observation? We need to observe the three things. So I'll just, okay, so we need to observe the three things. The first one is T P. Okay, so first one is TP, and second one is T P low to high. Okay, so TP low to high, and next thing is TP high to low. Okay, so these three things we need to observe. Okay, so this is not TP, this is TD. Okay, that delay, and here TP low to high and high to low. These three things we need to measure. Okay, so now, so how to measure this TD? So for that one, the first thing is click on this V in. So here you will get one cursor here. Okay, so one cursor, we are going to get some cursor here. So just bring this cursor to the V in's 0. Okay, complete 0. Let's zoom this. Just bring this cursor to the complete 0. You can zoom like this. Okay, so here we have only one cursor. Just bring that cursor to the complete 0. Okay, it is selected two cursors. Two times I clicked. Okay, one time click on this and just bring this to the complete 0 of the V in, and click on the V out. Okay, so here we are going to get the, okay, so what you can do means, okay, now it came, the two cursors are there, V in and V out. So like this, the two cursors we need to get. So this is the cursor 2 that you just keep in the V in's complete ending, any of the cursor. Okay, another cursor 1 we need to, okay, so just click where, okay, just zoom this. So wherever this, okay, so here you can see this is 5 volt till here, this is 5 volt till here, then it start to decreasing, that is, okay, so here you can see it is 5 volt till here 4.99, then it will start decreasing. Okay, then it will started decreasing. So here till what time it is 5 volt. Okay, so yeah, 113. Okay, so what is this value? 113.67 picosecond. So that is the TD value, simply we can write. So it is 113.671 picosecond. Okay, so now TPLH means low to high. Click on this low to high. So what we do means, so just zoom this V out. Okay, for some part you just zoom low to high from this low. So just click on this and take, where is the cursor? Okay, so cursor V out. So this is the cursor, and just click here. Again you click here, another cursor, just take here somewhere and zoom this part. Then take this cursor 1 from low to high, right? So from low, that is it has to be 0. Okay, so yeah, this is okay, so 0, then low to high. So at what point this will going to be, okay, cursor 2. So at this point. Okay, 4 point okay, we'll consider this as high, 4.9 and something. So here the time is, okay, so yeah, this one and this one. So this is 11.2 nanosecond. Okay, so this is, okay, this is now exactly converging. So this is difference. Okay, so difference we need to take. So this is 3.096 nanosecond we are getting. Cursor 2 minus cursor 1, right? Yes. So this is this okay, so how many seconds we are getting? So this is from here to here, that is horizontal, so it is 3.096 nanosecond. So this value we need to get 3.096 nanoseconds. 3.096 nanosecond. Usually this TD will be in picosecond and this will be in nanoseconds. Then this is the TPLH and TPHL. So high to low, just bring this to high. Okay, high values, directly bring high, and this to the low here. Okay, so exactly, okay, low. So then here 1.8322, so this one we just need to paste here. Okay, only this much value is enough. So this is for the one case. So similarly we need to find for Wn is equal to 2 times of Wp, 2 times of Wp, and even for Wn is equal to Wp by 2. Okay, so Wn equal to 2 times of Wp. So for that one, simply go to, no need to change in that layout and all, that means schematic and all. So here we have the NMOS, Wn is equal to 2 times of Wp. That means Wp is 2U. So here we need to make this as a 4U. Okay, then click run. So now let's observe the waveform. The delay has to change now. So one is, it is already there at TPLH. Let's zoom this, and it is make proper alignment to this one, and here okay, so this is 1.61 TP. What is this? This is TPHL. Okay, this is TPHL. So for this condition, so TD we need to find, TPLH we need to find, TPHL 1.16. so here we can see this is little bit more and this is little bit less, and TPLH, so that is low to high. So for that one we just need to low to high, we will see here. So this is 1, I need to keep it to the lower point. Okay, so this is lower point and this is at the higher point. Yeah, so now the delay is 3.2172. so this is okay. This is slightly increased. Okay, then let's go to the TD, and in the TD, so go to the starting of the, okay, so cursor, okay, we just delete these cursors and click on the V in, that is one cursor, and another click on the V out, second cursor. First cursor we need to keep at the here 0, and second cursor, okay, so first cursor we need to keep at the 0, and just zoom this part, and the second cursor we need to keep at, okay, so again just zoom this part, and here, okay, so where it just start decreasing at this point, so 121 point, okay, we got the more T here, okay, 121, and similarly find for this one, and comment down for which configuration there is a very less delay, or for which configuration there is a more delay. So just comment it down below. I hope you understood this. In the next video we will see how to construct the layout for this schematic of the inverter. Thank you.